Hi everybody, welcome back to Socsci10 Statistics, Spring 2021. I know this is the last week of class, and you got your test tonight, and you also have your final. So let's not forget next week that we have a final, and the final is cumulative. Okay, so we're going to talk about just briefly about the last parts of the book that you have to read, which is this multinomial and hypergeometric distributions. Now, if you recall from last week, we had the binomial distribution, and the binomial distribution gave us a formula, and this formula is incredibly useful. This formula tells us how we can compute what the probability is of a particular mixture of samples coming out a certain way when there are two options, right? Like you're sampling from an urn, and it could contain balls of one color or another. You get red balls and blue balls. And you pick a ball, it could be red, it could be blue, and you want to know, if I pick so many balls, how many are going to be red? What's the probability that so many are going to be red and so many are going to be blue? You have multiple outcomes. In this case, in the binomial case, you have two outcomes. Well, now we're in a situation where, what about if you have three outcomes, right? And in the book, they talk about a situation where you might end up with a yes, no, and a maybe. The situation they analyzed in the book was of a chess match. So chess matches can end in a win for one side or the other, or a draw, right? Sometimes they end in a draw. It doesn't happen all that often, but it does happen. And at the expert play, it happens a lot more often than it does in novice play. So you have to take these into consideration. That's three possible outcomes there: win, lose, or draw, right? So you can't use the binomial distribution for it anymore, right? Because there's more than two outcomes. So now we have something called the multinomial distribution. What this formula does is it's going to help you calculate what the probability is you have multiple mutually exclusive outcomes. All right, and each outcome has its own probability of happening. And this formula, as you can see, it is extendable to k number of outcomes, right? In actuality, if you look very closely at this formula, it is actually a special case. It is a generalized case for the binomial. So the binomial formula is specialized for the situation where k equals 2. And if you put k equals 2 in here, you're going to get the binomial formula. But this is a more generalized formula for k possible outcomes, and it can be used for any number of possible outcomes. Okay, so you can see the formula here. They talk about it in the book using the example of chess matches where you can get a third outcome, you can get draws. But basically for each outcome, you've got the total number of events, right? And then for each outcome, you get the probability that that outcome can happen, right? And then you have the number of times that outcome happens in your sample, when you take your sample. And you're going to compute the probability of that, right? And this formula, which is easily extendable to any number of k, can compute that for you. So that's the multinomial distribution. All right. So now we got that out of the way. We're going to switch gears a little bit, and we're going to look at the hypergeometric distribution. Now, what kind of distributions are these? These are distributions for without replacement. Let's say you draw a card from a deck, and you're going to draw another card, but you're not going to put the first card back in. This is actually, think about it, this is classically the way cards are dealt. If I deal you a hand in poker, I don't, after I give you a card, put that card back in the deck and deal you another one, right? The deck is reduced as I deal the card out. So that's without replacement, is when we don't put the cards back in. And we're not replacing the cards. So the probability mix of what's in the deck changes, right? How can we compute that? Aha! Well, we have something called the hypergeometric distribution. And the hypergeometric distribution, it is really concerned about this kcx, which is a number of combinations of k things taken x at a time. So you could have the alphabet. There's 26 things. That could be your k. And you're going to take 5 letters from that alphabet, right? So if I take a random 5, how many different ways could I take the random 5 letters of 20 out of the alphabet of 26? So that would be 26 choose 5, right? In this case, in kcx. And you see those combinations showing up in this formula, right? The rest of the formula is also pretty straightforward in that k is the number of successes in the population in general, right? And number x is the number of successes in the sample, right? N is the size of the population, and little n, small n, is a number sampled. So you got to make sure you differentiate between what the big N and the small m is standing for. But you can apply this formula and you can get the probability of an event occurring where you're not replacing the item into the deck, where the item is changed, right? So what you're saying here, like K choose X, if I choose 5 letters out of a 26-letter alphabet, right? But if I choose A, I don't put A back in and say I'm going to choose another letter A. You know, having 5 A's in a row, it's not what they're talking about here. What they're really talking about is, you know, give me 5 distinct letters. You can't choose the same one twice, right? How many possible combinations is that? And that is your KCX. And that is basically what is going on with these hypergeometric distributions. This is how you calculate these kind of probabilities. Now the homework for this week just looks at the last questions in each of these chapters, each of these sections of the book. Just have one question. So you're not going to go to the end of the reading and look for questions there. You're just going to go to this section. At the bottom of the section is a single question, and that is the homework question for this week. All right. Best of luck on the homework, the test, and the final. And don't forget, we're dropping a lot of the bad grades. And I'm sure that mercy will be shown where mercy is due. So wouldn't worry too much. It's a little late to worry now. But make sure you study. Make sure you know these formulas. They're not so hard to memorize. But the best way, of course, to learn math is to make sure you do all the homework. And to always go to all the lectures, watch all the videos you can. But the practice and the homework will build an intuitive understanding, and that is the best preparation for the exams. If you haven't done the homeworks and you want to study for the exams, well, that's the best way to study for the exam, is to do the homework. So I recommend doing the homework, and I recommend submitting that homework also, if you do it. All right? And best of luck, and I hope you enjoyed your quarter and Socsci10, and I hope you guys progress well into the next chapter of this course, or elsewhere in cognitive sciences, as the case may be. So enjoy your summer. Signing off.